So, in the last two lectures, we saw applications of two algorithm design techniques in the dynamic setting. One was the principle of monotonicity, the other one was random sampling. So, in the next 3 or 4 lectures, we will see more examples of the same two techniques, but in the context of a problem known as dynamic connectivity. So, I am going to present 3 or 4 different results on this problem, but just keep in mind that all those results will use either the monotonicity principle or just random sampling and some Chernoff bound. Okay. So, what is dynamic connectivity? As stated here, you are given as input an unweighted undirected graph with n nodes and m edges, and now the updates operations that your data structure needs to handle are insert an edge into the graph or delete an edge from the graph, and the queries will be given two nodes u and v, are they in the same connected component. Okay. So, ultimately what we are going to show is there are two results. In the deterministic setting, we will give order polylog n amortized update and query times, and in the randomized setting, again we will get polylog n, but in this case worst case update and query times. So, you can immediately see one difference between this problem and the shortest path problem. For the shortest path problem, our update times were quite large, n. Here it is quite small, polylog n. Okay. So, before moving on to the general problem, let us consider a special case to build up some intuition. Suppose we want to build an algorithm for dynamic connectivity on paths. Dynamic connectivity on paths. So, these are special classes of graphs. So, the query remains the same, are two nodes in the same component, but now suppose the adversary guarantees you that each connected component is a path. So, what will the update operation look like? So, when you are saying that insert an edge, it will look like this. You are given two paths and you are asked to insert an edge between u and v, so that these two paths will be merged. What will the delete operation looks like? So, you are given one path and now you are asked that okay, just delete this edge, so that you will get two new components, this one and this one. And when the query comes, you just need to answer whether these two nodes lie on the same path or on different paths. So, now I claim that this problem you can solve if you have done an introductory course on data structures. Can anyone see the answer to this? But union find is only for edge insertions, right? Okay, that is a good point. We will come back to union find data structure in a moment, but note that in union find you are allowed only to merge two sets, but here you are given one set and it is getting split up into two, right. So, the answer is just maintain these paths as balanced search trees. So, basically this is the answer. maintain So, now when the query comes, what will you do? First of all, there are two nodes on a long path, you just need to ask whether they belong to the same search tree. So, you just traverse to the root and check if the root is the same for these two search trees. So, query will take log n worst case time. What will you do for the updates? First of all, insert. For this thing, it is as if you have this sorted list and you have this sorted list and you are appending this sorted list at the end of this list. Okay. So, this operation you can perform using a balanced search tree, as you would know from a data structure course. So, insert is simply merge two balanced search trees. This is also order log n and again worst case. Okay. What is delete? For delete, basically you have this sorted list and you are splitting it into two halves. The first half is this one, the second half is this one. So, delete operation will just be split one BST. And this is also known to be in order log n time. So, basically you can solve this problem on paths in log n worst case update and query times. Yeah. So, the query is two nodes, are they in the same path? So, each path is stored as a balanced search tree. So, now what you do for each node, just find the root of the corresponding tree. The depth is log n, right. So, you can find the root in log n time, then check if the two roots are the same. Correct? Okay. The next observation is, let me get back to what Niranko suggested, dynamic connectivity in incremental setting. Okay. Under edge insertions. So, now we have a general graph, not paths, but the constraint is that you only allow for edge insertions. Okay. Edges will never be deleted. How will you solve this problem? Anyone? Basically maintain in each component a spanning tree. Okay. So, the first step is that maintain a spanning forest, maximal spanning forest. Okay. You do not even need to go there. Why do you even want to maintain spanning tree? It is just edge insertion, right. So, basically you have two components. Each of these components just is a set of nodes, and now if the edge insertion joins two nodes in the same component, you do not need to do anything, right. The only thing is that when the edge insertion joins two nodes into different components, in that case what you need to do? You just need to merge these two components, right. So, this dynamic connectivity under edge insertion reduces to the problem of merging two sets S S prime, this is in this case, and the other thing is are two nodes U V in the same set. Sorry. Now, this is precisely what the union find data structure will do, right. So, just use union find. And you get order alpha in time. Alpha is the inverse Ackermann function. Okay. So, now the next special case is going to be dynamic connectivity on trees. So, in this case the adversary guarantees you that each connected component will just be a tree. Yeah. Yeah, of course, but you will get no. 1 second. Yeah, you can just build an arbitrary list of these nodes, and then when you are merging two sets, you just merge these two lists. So, basically it will give you log n update time, but union find will be faster. Okay. So, basically whatever union find does, you can also do it using balanced search trees. Okay. So, dynamic connectivity on trees. So, the adversary guarantees you that each component in your graph is a tree. So, then what will the insert operation look like? You have two trees here like this, say, and now the insert operation says that u is in one tree, v is in another tree, and you are inserting this edge. So, these two trees will merge. Okay. Now, this much you can do using balanced search trees, but the delete operation will become complicated. So, delete is you are given a tree, need not be a binary tree, but anyway. Now, I ask you to delete these two this edge u and v, so that this will split into two halves. Okay. The question is, point is, if you were maintaining this as a list, u and v need not be consecutive elements in the list, right? And there might be many other elements in between u and v, some of which belong to one side of this edge, some of which belong to the other side of this edge, and it is not at all clear how will you then split this list. Clear? Okay. So, now a data structure that handles these insert and delete operations on trees and answer these connectivity queries is called a dynamic tree data structure, and there are several of them available in the literature. Okay. But we are going to just consider one of them, the simplest one of them. It is called ET trees. ET stands for Euler 2. Okay. So, as the name suggests, what it will do is, it will convert this problem on trees into a problem on paths, on merging and splitting some lists, so that then you can apply the binary the balanced search tree data structure on it, right. So, now the point is, given a tree, can you construct a list out of it? that in some sense will be easy to split as the tree is getting split. The merging is easy. If two trees are getting merged, you can of course merge two less. Okay. So, just spend 1 minute on it. You are given a tree, can you come up with a linear ordering on the nodes, so that when an edge gets deleted, you get two new trees. The two new linear orderings can be obtained by splitting the initial linear ordering. Is the problem clear? You think about it for one moment. I will just go ahead. So, look at what is happening on paths. You are maintaining this ordering on the nodes, and then when an edge gets deleted, this path gets split and you get two new orderings, right, two new paths. But these two new orderings you can get by splitting the old ordering. Okay. But this will not hold for a tree, right. Given a tree, if you come up with an arbitrary ordering on the nodes and then the tree gets split, you will get two new trees. It is not easy to get the nodes on these two new trees by splitting the old ordering. I am asking you, how can you do that? Okay. Okay. So, let us think about it for one moment and erase this part. So, the answer is just consider an Euler tour on the tree. So, what is an Euler tour? Let me just draw some random tree. Okay, and let me just name them, say A, B, C, D, E, I. So, to get an Euler tool, you first root the tree at an arbitrary node, say A, and then just make an in-order traversal. So, basically you first traverse this edge, go back and again come back to V. It will be like this. So, it just traverse in this direction. So, is this clear what is happening? So, basically in in-order traversal, you just first pick one child B, visit all the nodes rooted at this subtree recursively, then come back to A, then go to the next child, visit all the nodes rooted at that subtree recursively, then come back to A and go proceed in this fashion. Okay. Okay. So, now the point is yes, you will be storing one node multiple times, but the total number of nodes, total number of times you will visit the node will be equal to 2m, because each edge you will traverse in two directions. Okay. So, for example, let me just draw one other random tree that is easy. A, say B, C, D, E, yeah, let us suppose this is the tree. So, if you root it at A, what will be an Euler tour? An Euler tour will look like this. So, first you go to A, then B, then C, then again you come back to B, then D, E, then again you go back to A, come down here, this is F, G, F, H, A. Yeah. This need not be binary, yeah. And the tree need not be rooted, but to construct the Euler tour you just arbitrarily take any one node as a root and then come up with this list. Okay. So, now observe that suppose I tell you that this edge is being deleted, BD is going, okay, let us make it a little bit more interesting. Let us say this edge is being deleted, AF. Okay. So, after this deletion you will get two new trees, right. What will be the Euler tour of these two trees? Sorry, F H and then again it will be F before you come back to A. There was a mistake here, right. Sorry? Let me come up with the correct list, sorry. Okay, so A, from A you go to B, then C, then you come back to B, then you go to D, then E, then again D, then you go to B, come back to A, then you go to F, G, come back to F, H, come back to F, A. Now, it is clear, right. Okay. So, now suppose this edge is getting deleted. So, you will get two new trees, right, and suppose the old, for this half you root the new tree at A and for this half you just root the new tree at F. So, what will be there to the two lists? Just look at the first occurrence of F and last occurrence of F, just take this thing out. Okay. Take this thing out from the list. So, basically this will be the Euler tree rooted at F. Okay. And how will you adjust the previous Euler tree? Basically, after you have taken this thing out, you will see that this node A appears consecutively, right, and this is a mistake. I mean, A should not appear consecutively. So, basically you just delete one A arbitrarily, and this applies in general, as you can observe. Okay. So, then the thing is this, how will you represent this as a data structure? First of all, for each node, say this guy is A, right, you maintain two bidirectional pointers that point to the first time A appears in the list and the last time it appears in the list. Okay. Now, why is this needed? It is needed because when you are splitting this edge, you need to find the first occurrence of F and the last occurrence of F, right. How will you find that? That is why you will need these two pointers. Okay. So, using these bidirectional pointers, you will be quickly able to identify the first and the last positions of the subtree that are being splitted, and then you just perform one split operation. So, here you just split this list into this half and this half and this half. So, there will be three new parts, and then this middle part will become the Euler tree for the new subtree, for the new tree, and then you need to just patch up these two parts on the two sides. Is this clear? I am not writing the pseudo code. Yeah, go ahead. Oh, okay. Maybe you don't need bidirectional pointers. Yeah, by bidirectional I mean this is a list, right. So, when you are looking at one element in the list, you need to know which node it corresponds to. In that sense, it is bidirectional. So, you are just maintaining a list, right, and okay, maybe you do not need bidirectional, just ignore that part. But you, for each node you do need to find the first and the last positions of that node in that list. Okay. Okay. So, basically Okay, one other thing, let us come back here. So, this is for delete, right? This is how we will handle a delete. Now, what will you do with insert? Let us just do a simple example. So, this is 1. Okay. So, suppose this is A, B, C, D, E, F, G, and suppose these are the roots A and F, these are the roots. Now, if I ask you to insert this edge A, B, then it is relatively easier, right, because what will you do? You will just append this list at the end of this one, okay, and you just have to adjust for the last occurrence of A. That is just one minor technicality. So, basically just look at this list. So, this is A, B, A, C, D, C, E, C, A. This is the list, right? And for F, it is going to be F, G, let me write it here, F, G, F, I, H, I, F. So, now I ask you to insert this edge A, B. What will you do? Just pick the last entry apart, then insert this thing. So, suppose these are the 2 blocks, 3 blocks. Okay. This is say B 1, this is B 2 and this is B 3. So, your new list will simply be B 1, B 3, B 2. Oh, sorry. No, you do not do it with B 2. You just append an A at the end of this B 3. That is what you will do. Suppose this is what your B 1, this is your B 3. So, your new block will be B 1, B 3, A. Correct, right? Okay. But the point is, suppose I now say that I am inserting this edge from A to G and G is not a root, or say from C to G. And C and G are not the 2 roots of the tree, and it is allowed, right, because the adversary does not care about which node you have chosen as a root. The trees are unrooted inherently. Okay. But in this case, you notice that it is this, from these 2 lists, it is not obvious how to get the merged list. Right, because the point is this, suppose you want to insert this list inside this one, you might find the positions of C. So, this is the first position of C and this is say the last position of C. So, what you will say is that okay, from C I will insert this list before coming back to A, but this list rooted at G looks a bit different from the one that is rooted at F. But for that, what you need to do is you just need to reroute this tree. So, you need to have one operation that takes a tree and just roots it at a different internal node in the tree. Okay. So, say reroute this tree that is rooted already at R and root it at V. But this operation just again can be performed on a tree just using one cyclical shift. So, basically if you instead of starting at this root, if you are starting at this root, you can get the new list using either some merge and split operations on the list or one shift operation. Okay. So, let us just verify quickly how will you do this thing. But is it clear that for insert you just need the rerouting operation, which you do not need for delete. Okay. So, let us say we just have this one. this tree. So, the list is now A, B, A, C, D, C, E, C, A, and now I ask you to reroute it at C. So, basically what will happen is, say this portion is B1. So, you can start with B1, right, if you are rerouting it at C. You can start with this part first, and then you are going back to A, then coming back to B, and again going back to A, right. So, after B1 it will be A, then you are coming down to B, then you are again going back to A, and then it is C. But this part is already present here. So, basically if this part is B2, it will become B1, B2, C. Okay. But you can just check out exactly what is happening. It is not very difficult to write even the code for this. Okay. I did not have the pseudocode in mind, but the point is that you can also reroute it using balanced search trees. So, this is basically ET trees. So, root each tree at a arbitrary node, store the Euler tool, as a balanced search tree. This is all it does. And this will have order log n worst case update and query times. Okay. Now, we will move on to consider the general problem. Even erase this. But we will still need Euler trees, sorry, ET trees. Okay, so, what is the general problem? Now, there are no trees, there is only graphs. Okay. What is the most natural approach? For each connected component, you maintain a spanning tree. Okay. Then, when an edge insertion occurs, you can handle it using this ET tree data structure, right. You just check if two endpoints belong to the same tree. If yes, nothing to do. Otherwise, if they belong to two different trees, just merge them using the tree data structure. So, the hard part is to handle deletion of edges. Okay. So, just insertion can be handled by ET trees. Even for deletion, so you are maintaining these trees, right, and so just have this picture in mind. Each tree corresponds to a connected component, and the non-tree edges all belong to the same connected component. So, there will be some non-tree edges as well in this graph, right. These are, I am represented using these dotted lines. They all will go to the same connected component. There will not be any crossing non-tree edges. So, now if a non-tree edge gets deleted, again there is nothing to do, right, because you are still maintaining the maximal spanning forest. So, handling non-tree are easy, and the hard part is handling tree edge deletions. So, basically one tree edge gets deleted, it is not obvious how you can handle it using your ET tree data structure, right. Because what ET tree will do is ET tree will split this into two new trees, but maybe these two components are still connected, you just need to find this non-tree edge and patch this thing up. So, suppose this is a tree that you are maintaining, the bold edges are the tree edges, and now I delete this tree UV. Let this subtree on the U side be called TU, and let this subtree on the V side be called TV. The ET tree data structure can give you TU and TV, but the hard thing is to check whether there is a non-tree edge that crosses TU and TV, and if there is an edge like that, say AB, insert this edge AB into to merge TU and TV in the dynamic tree data structure, that is what you need. So, as you can see that at least one half of the job would be to check if there is a non-tree edge incident upon somewhere in TU, not necessarily crossing. Okay. And we need to augment the ET tree data structure to handle this operation as well. So, what will be the operation that we need to handle? Let me just write it down here, so that after deleting tree edge U comma V, say report the non-tree edges incident upon TU in time, say order log n number of such edges. So, what I am saying is that trying to convince you is that we need to have this more general operation on the ET tree data structure, so as to handle the general case. What this operation asks for is that I am splitting a tree into two halves. After that, I just get two new trees. Take any tree TU, just give me all the non-tree edges incident upon TU. Some of them might be going to some other component, some of them might be inside edges, I do not care. Just give me all the edges one after the other in time roughly proportional to the number of such edges. If there are many of such edges, of course, this will take longer time, right, but for to report each new edge, he will take at most log n time. This is the operation we want. Okay. And just stop me here if you do not feel convinced that this is a natural thing to ask for. I mean, at least we will need some such operation to handle the general case, right. So, is this operation clear what we want? So, the operation is you just have this dynamic tree data structure, it supported merging of two trees, splitting of two trees. In addition, there will now be some non-tree edges, and the operation asks, given a specific tree in this data structure, just report all the non-tree edges incident upon it fast enough. Okay. So, now I am just going to pose this problem, formulate this problem as a more generalized dynamic tree data structure. So, the problem is this that we want to solve using ET trees. You are given a set of nodes, this is fixed. Now, there are two types of edges, say F, these are the tree or forest edges, these are the non-tree edges. And now, the update operations are you insert or delete an edge from F, or you insert and delete an edge from E. The guarantee that is given to you is F is a forest always, and the query is report all the non-tree edges, say incident upon a given tree in this forest. And a non-tree edge is incident upon tree T if at least one of its endpoint is in T. Okay. Now, how can you do that? So, note that insert delete F that you can handle using ET trees. For insert delete non-tree edges, the idea is actually not too difficult. So, basically each ET tree corresponds to a list, right, say C, D, E. So, this corresponds to a list A, B, C, B, D, B, A, E, A. Now, if suppose I insert an non-tree edge in E incident upon B, its other endpoint might be anywhere, I do not care. Okay. Let this edge be E1. What you do is, let us pick the first occurrence of B in this list, you just associate a token with it called E1. And suppose I delete an edge, this edge E1, what you do? You just delete this token. So, now the thing that you are maintaining is just a bunch of sorted lists, where each entry can potentially have one or more tokens. So, now inserting and deleting a token corresponds to inserting and deleting a non-tree edge, but that is easy, right. You are asking that insert or delete this token into this element, you just go to that element and insert or delete that token. But what is this operation? Report all the non-tree edges incident on T. It just says, given a list, report all the tokens associated with its elements. Okay. But you cannot afford to visit all the elements to do that, because there might be n elements in this list, but only very few of them have tokens and there are very few tokens. Okay. So, how will you do that? The point is that these lists are represented using balanced search trees. This is the data structure exercise sort of. So, basically it is a generalized balanced search tree operation where the elements can have tokens.
What is the meaning of inserting a forest edge? I mean, you already have a spanning tree.
Oh, inserting a forest edge meaning you are merging two different trees that are in two different components.
Okay, but how do we know whether it's in F or in E before?
That is given to us. I am not claiming that this will solve the dynamic connectivity problem. All I am claiming is that this will have a feature that will be very helpful in solving the dynamic connectivity problem, because you can think of the dynamic connectivity problem as being decomposed into two halves. In one half, you are just maintaining these trees corresponding to these components. In the other half, when a tree is getting split, you are looking at a subtree and you are asking for the non-tree edges incident upon it. So, I have just decomposed it into two halves, as if somebody externally tells you that okay, just maintain these forest edges, that is one part, the other part is the non-tree edges, and these two are distinct from each other. Okay. We will later use this data structure to solve the general problem. Is that clear? Okay. So, how will you do this? So, it is as if a balanced search tree you have to maintain, but each element can have a token. You will be asked to merge and split two search trees, and in addition you have a one more query. Here is the root of this subtree, here is this root of this tree, report all the tokens inside this tree. So, the idea is very simple, right. So, this is going to be a balanced search tree. Suppose it is stored like this or something, I am just ignoring this A, right, and say this is the root. So, basically at each internal node, say x, you just store a yes no pointer, there is just a yes no bit. If this bit is yes, it means there is at least one token somewhere in the subtree rooted at x. Is this clear? So, you are building a balanced search tree on these elements. At each internal node of that subtree, store a token that denotes whether, if you just look at all its descendants, will you find any token there. If there is no token in this descendant among these descendants, then it is no. Okay. Now, suppose you are maintaining these bits at each of the internal nodes. How will you update them? We will come back to that later on. Yeah. It is this ordering. Yeah. No, because we need to merge and split this list using our ET tree data structure, right. If you use the number of tokens as your ordering, when a particular tree is getting split, how will you patch it up? Does this make sense? Okay. So, these bits you are storing, and how you are updating these bits, we will come back to that later. But now, suppose you have these bits, and now the query comes, given this tree, report all the tokens. Then you can do this thing efficiently in exactly this thing, right, in time order log n times the number of such edges. Why? It is as if you are starting from the root and you ask each of its children that is this bit yes or no. If the bit is no, you do not need to traverse that subtree anymore, you just abort there. If that bit is yes, you just again go to that next child and again ask this question. So, basically you will be able to abort a whole bunch of subtrees that you do not need to traverse, and you can check that the time will be order log n times the number of such edges, because the depth of this tree is at most log n. So, suppose there was only one token associated with some element, then how will these bits look like? This bit will be set to yes only on the path from the root to this element, and everywhere else this bit is set to no. So, you are just as if following this path and finding this element, and it is taking log n time, and it can be generalized even if there are multiple tokens floating around here and you are just using these bits. Okay. Now, final question is, how are you going to update these bits? That is easy, right? Suppose a token is inserted in this element, you just update the whole path to the root, and a token is deleted from this element, you just update again the whole path to the root, and again the depth is at most log n. So, this also you can do in log n time. Okay. Mm-hmm. Yeah, if there are two tokens for one element, right, and you deleted one of them, you do not do any update, because this yes no bit just represents whether you will find at least one token there.
So one parent has two children with tokens on both of them, then
No, then also you just do the following. Okay, let me do this. Okay, let us just change this thing. Instead of yes no bit, let us say you just store the number of tokens you will find there. Is that fine? So, now when you are inserting one token, you just look at this path, you just increment this values by 1. Let me just erase this thing. Number of this x will be number of tokens in subtree and when you are deleting a token, again just consider this path and delete everything by decrease everything by 1. Yeah. So, what he was suggesting, but even with bits I think it will be fine, because what you are suggesting was this, right. Let us just work it out. Suppose there is u v, okay, let us just say x y z, okay. Sorry. And suppose this was 1, by 1 I mean yes, the bit here was 1, the bit here was 1, the bit here was 1, and now there was this path from y, and here you deleted one token. You first observe if this guy has non-zero tokens. If this guy still has one token, you do not need to update anything here, right, correct. So, suppose this guy now has 0 token. So, you just need to now decrement this guy, and you are traversing up here, and suppose you decrement this. Then when you go to x, what will you observe? You will observe that x has 2 child, one is now 0, the other one is now 1. So, you will keep x at 1 and just will not traverse the rest of the path to the root, because now from x till the root, of course, you are guaranteed to have one token. Is that what you had in mind?
before updating we have to look at both the children.
Yes. Okay. But again, the exact detail is not very important. The point is that you can actually report the non-tree edges incident upon each tree in the Euler 2 tree data structure. Okay. Okay. Now, I will conclude by giving the intuition for the general case, and then in the next class on Thursday we will go into the actual algorithm. So, we want to solve the general problem. what we have observed is this, that insertion only setting is easy, right, because then you can just have, yeah.
What happens so when you introduce this extra edge, right, to merge these two things, how do you construct this binary search tree for this?
Here, that is what you do using this ET tree data structure, right, you merge the two lists.
What about this yes to push rules? Is it here or it takes long?
The point is that this yes no tokens, say for example, basically when you are splitting out a part of this list, okay, from this main list, what will happen? Just look at the subtree where this thing is rooted, everything will remain unchanged in this subtree, right. So, the only thing that you need to update is from x to the root, and this just path of length log n. So, you can just see what information is stored in this subtree and update this path, and then you are done. If you get constantly many pieces, then you are doing that thing each time, right.
How many pieces would your tree break into when you merge two?
Let us just consider the split first. Suppose you are deleting one edge. So, deleting one edge can be fixed using the ET tree using a constant number of splits and merges, right, that we have observed, right. So, there will be a constant number of splits and merges. If we can show that for each split and merge you can update these tokens in log n time, then you are done, right. So, therefore, I am just focusing on one split, and can you convince yourself that for one split it is easy to update the tokens. Why? One split just looks like as if you are isolating out one portion of this list, and similarly you can see that one merge, and then of course, you have to rebalance it, that will be taken care of in the balance search tree data structure. Okay. And you can also show that one merge, for one merge again, since the depth is at most log n, you can adjust these tokens in order log n time. But then again of course, there will be rebalancing within the balance search tree data structure. So, you just visit each step that will be performed in this rebalancing operation and just verify that these tokens can be updated. Okay.
You get a new list, right?
Mm-hmm.
This new list will have a new, at least it will have a distinct search tree, balance search tree.
Mm-hmm.
So, is it clear that that search tree will come from these two search trees by merging them?
Yeah, how it will work is, first you merge these two subtrees, okay. Then you get a proper tree which is unbalanced, correct? Yes. So, that is what I meant. So, when you are just getting this tree by merging these two things, then you can update these tokens. Okay. The next part will be to rebalance that new tree.
You think that rebalancing will take log n, order log n?
Yes. Even just for the merge itself, to adjust the tokens, you will take log n time. So, okay, forget about the tokens. How will this thing work when you are merging and splitting two lists? How does balance search trees work? You just visualize it like this. First, as if you are just merging and splitting two trees, and then what you are getting is an unbalanced tree, and then you are rebalancing it. Okay. Now, how you are rebalancing it will depend on what tree you are using. Now, what I just wanted to point out was that during the initial merge and split step, you can update the tokens using log n time. And then what you have to verify is, take your favorite implementation of a balance search tree, look at each rebalancing, each unit elementary step that it is performing. You can preserve these tokens for every unit step. Okay. This is just a data structure exercise. You can just verify that it will work out. Okay. So, let me just give you the brief intuition. We want to solve the general dynamic connectivity problem using ET trees. What we have observed is edge insertion is easy, because it just corresponds to merging two ET trees. We have also observed that a non-tree edge deletion is easy, because you do not need to change anything. The only hard part is this, handling tree edge deletions. Okay. So, just to get a brief intuition, let us just focus on deletion only setting, where you are just deleting tree edges. Okay. It is as if the adversary is trying to make the life worst for you. This is just an intuition, not a formal proof. Do not take it too seriously. I will give the formal proof in the next class. So, just consider a sequence where you start with a graph, you have your ET tree data structure, and then what adversary does is at each time step it just deletes one tree edge. Okay. So, then how do you see at least some rough idea as to you can handle all those edge deletions in log n amortized update time? Sorry? Yeah, go ahead. What is your solution?
You can access the tokens corresponding to the edge that is being deleted. That will, and then you have to also check that. Okay, so no, first split the ET tree into two halves.
Let us just draw this picture. Okay. So, this is U and V, and suppose this is T U, this is T V. So, you just get these two new trees, T U and T V, but then what you need to do is you need to check, you need to check if there is a crossing edge. Do not think of it as tokens, I mean the token thing was just for the data structure. Okay. A crossing non-tree edge, this is one you need to find, right, and note that it is not necessary that that crossing non-tree edge, if it exists at all, will be incident upon U or V, it can be anywhere in between. Okay. Now, suppose you do the obvious thing. First, you just ask your data structure, give me all the non-tree edges incident upon T U, that it can give, right. But the point is that many of those edges might be of waste, because you see that those edges are in edges, I mean both of the endpoints belonging to T U. But you just parse through this list, and the moment you find one edge that is going out of T U, whose other endpoint lies in V, you just pick that edge. What will you do? Say this edge is x y. First of all, this edge you will insert it into your ET tree data structure, so that these two things get merged. And the second is that this edge will no longer count as a token, right. Earlier this was counting as a non-tree edge, so delete this edge as a token from x and y. Okay. Now, what is the bad instance for this algorithm? Suppose this is what you are doing. The bad instance is that each time you go through these non-tree edges incident upon T U, and there are a lot of them, but each of those turn out to be bad edges, meaning it turns out to be that the edges that you are actually parsing through, they have both endpoints in T U. And there are a lot of these edges, and you are spending a whole lot of time, but doing no work at all, I mean no effective work at all, right, because, and then you exhaust this list of all these non-tree edges that are bad edges, and then finally you discover that, oh, actually there is no edge going to that part. So, you could have just handled it in constant time, you could have just said that, okay, I am just deleting this edge from my ET tree data structure, and it stopped, not constant, log n time, but you potentially spend E amount of time where he is the number of such bad non-tree edges, and there can be a lot of them. That is the bad case, right. So, can you see that this bad situation cannot happen again and again? So, the point is that what can be the worst case running time here? The worst case running time here can be order m, because there can be m such bad non-tree edges that you are going through, actually tilde O of m. Okay. But if after each edge deletion you are spending order m time, then the amortized update time is order m. But what I claim is that this cannot happen too frequently. So, the observation is this: each time this is happening, this is the crucial part. You picked the tree that was of smaller size. So, there were two trees that you could probe for non-tree edges, and it is sufficient to probe any one of them, right, because if there is a crossing edge, it will be represented as a token in both of them. So, for probing you picked the tree that is smaller in size. Now, what does this mean? Suppose this is this bad edge, tree edge that you probed. You spent say unit or log n work there. Now, before this edge deletion UV, what was the size of the component x belonged to? It was Tu plus Tv, right. So, before deletion, the size of the component that x belonged to was Tu plus Tv. Now, after deletion, you did all this work going through all these non-tree edges, but in the end you were not successful in merging these two trees. But then after deletion, what is the size of the component that x belongs to? It is Tu, right. And by definition, this is at most by half. So, what does this mean? The amount of work you did here, ignoring the log n factors, ignore log n factors because we just want polylog n update time. Okay. So, the amount of work the algorithm does in this bad instance is proportional to the number of bad non-tree edges. Okay. So, let us try to amortize the algorithm's update time by the number of times the algorithm probes a bad non-tree edge. This is roughly going to be the algorithm's update time. Each time it probes a bad non-tree edge, it does some work that was not, that is redundant, right. There was no need to consider this edge. But the point is that each time this is happening, you know that the size of the component that this edge belonged to is getting halved. And this cannot go on for more than log n times, right, because initially it will be a giant component containing n nodes. So, you will be probing each non-tree edge that is bad at most log n times. Okay. And this is where the amortized update time will kick in. This will be the main intuition. And in the next class, I will just give you the formal data structure that. So, first of all, what I said was a very hand wavy argument, because I am not considering edge insertion, and I am just saying that consider just tree edge deletions. And then I also said that suppose this is the worst case that you could not find any edge to merge to. I mean, with all these assumptions I said give the main idea, but in the next class I will just present the full algorithm.